Okay, so if you're watching this, this is the lecture that I gave in class on Monday. So you were either absent or you were a distance learner. I'm going to try to fly through this so it's not super long. Essentially, I had you guys pull out all of your stuff, your notes and your worksheets, and I graded them. So if you're missing anything, I want you to go and check in on that and submit them as soon as possible. We reviewed the lab and bonds, and I'm going to give you a glimpse into the worksheet that you guys are going to do tomorrow on Tuesday. Ignore this. This was time to give to go over the lab. Ignore this one too. You guys don't have to use Pear Deck for this. I'm going to record the video on my screen and then make an Edpuzzle. Here I was just asking you to type in 2 patterns that you notice in the lab, so I'm going to make an Edpuzzle question right now for this. Okay, and then I'm going to go over the main patterns that you should have noticed in the lab. First of all, solids were not conducting electricity, but sometimes once you dissolve them in water, they did conduct electricity. The only no's that we got, some aqueous, however you want to say it, this just means dissolved in water. So your starting phase, was it a solid, liquid, or gas? Did it conduct electricity as a solid? Water soluble means did it dissolve in water? All of these should be yes, essentially. There wasn't anything that didn't dissolve in water. And then did it conduct electricity once it was dissolved in water? Your no's should be distilled water and sucrose, table sugar. Okay, so essentially the pattern we're seeing here is that solids don't conduct electricity, and in liquids they sometimes do. And then I asked you what type of bond, so what I wanted you to do here is answer ionic or covalent. And there was information about how you recognize this based on the electricity on the first page of the lab. Okay, the second pattern is that tap water conducted electricity, but distilled water did not. So just to go over this, what even is distilled water? Well, essentially, it's water that we distill and we make pure. And the way we do that is we take any type of water. This can be salt water from the ocean or tap water from the sink. We heat it up till it boils, and we have this liquid turning into gas or water vapor. We then collect it, and then we condense it in this condenser thing, and then we collect it in another container. So essentially it's a gas, a water vapor, and then it's condensed back into the liquid form, and then we collect it. So any impurities that were in the water before, any salts, anything like that, don't end up in the distilled water. And then I'm asking, what is in tap water that makes it conduct electricity? Well, essentially, this is way more of a biology concept, but it's good to know. Essentially, our tap water here in Hana, we pump it from the aquifer. So that is rain raining down on our island. The rain permeates through the soil in the rainforest and into the basalt rock layer that the island is. The basalt rock is really porous, and then we pump it up and we drink that water. Okay, so as it's making that transition from rain to being stored in the aquifer, it collects things along the way. It collects different stuff that is either in the soil or in the rock. The 2 most common things that it picks up here in Hawaii is calcium and magnesium. And those are just things that are naturally occurring in our rocks. So we call them minerals when we're talking about them being in water, especially like drinking water. So this is naturally occurring. It's good for you. You don't have to worry about anything. But essentially, that's why we see a electric current in our tap water. And we'll talk more about that in just a second. I'm asking you here, what can we conclude about the chemical bonds in tap water? Well, to kind of understand that, we need to first answer 2 other questions. Okay. One of the other questions on your lab was I asked you to draw the crystalline structure of NaCl. Why did I ask this? Well, NaCl, sodium chloride, salt, table salt, however you want to say it, it's ionic, and it's a perfect example of how ions bond. It is like the most iconic example. The one that you're always going to get the defined for ionic right off the bat. And that's because it's easy, it's simple, there's two elements, very clear transfer of electrons. So first we need to understand why sodium is ionic. Well, sodium has 1 valence electron, chlorine has 7. Chlorine wants to fill its shell, it's really close to 8, so it's going to steal this electron from sodium. And now it's going to have a full shell. Well, we lose this electron and we gain one here. So our new charges, we have a positive charge on sodium now, because remember it lost one of its negative charges, so it has a extra positive charge. And then chlorine has a negative charge because it gained one more negative electron. The way we write this in its solid form is just like this, NaCl. Okay, but what this looks like, the crystalline structure of the ion, well, you have to remember there's a plus charge with all sodium atoms in the compound and a negative charge with all chlorine atoms. If you're looking a top-down view, you're going to have repeating patterns of negative chlorine atoms, positive sodium atoms. Negative chlorine, positive sodium. But we actually end up with this three-dimensional crystalline lattice that looks like this. So you can, let's just pick this chlorine atom right here. We have a chlorine atom, it's got a negative charge, and it's surrounded by all these other positive charged sodium atoms, okay? So when I asked you to draw the crystalline structure, obviously something like this would be amazing, but I really just want to see something like this. Maybe try to make it three-dimensional, maybe try to draw a cube if you can. I know a lot of you are working on the computer, so it's kind of hard to draw, especially if you're not an artist like me. You guys have seen my drawings before. So this is like the key thing about ions, is that they're repeating patterns of positive and negative charges, and that's what holds them together, okay? Because opposite charges attract. So this negative atom is attracted to the positive atoms, and the positive atoms are attracted to the negative atoms. So that's what holds it in a solid form like that. Okay, now then I asked you what happens when you put it in water, and why does this happen? Well, first you have to understand covalent bonds, and this is the reason why I asked you this question, is because it's a comprehensive question. So essentially, here's our covalent bonds happening. Here's everything by itself. Hydrogen has 1 valence electron, oxygen has 6 valence electrons. When you put them together, they're sharing these electrons now, okay? So oxygen has a full shell of 8, hydrogen has a full shell of 2, because remember it only has 1, so it fills that first shell, which can only hold 2. So these are all nice and happy. The way we represent shared electrons is with a line like this. So this line represents, you can think of it as like connecting the dots. This line is representing, okay, hydrogen and oxygen are sharing 2 electrons right here. Same thing's happening right there, right here, okay? Then I asked everyone in class, using the pair deck thing, to circle the atoms that have, or circle the electrons that are being shared. So essentially, just to tell you the answer, these ones are being shared and these ones are being shared. And what I want you to notice here is that the majority of the electrons are spending the majority of their time around this oxygen, okay? And then the ones that are orbiting hydrogen are spending less time around hydrogen. So the majority of them are spending time around here, and because electrons have a negative charge, we end up with a negative, like partial negative charge on this side of the water molecule, and a partial positive charge on this side of the water molecule where the hydrogens are. So this interesting feature of H2O is so essential. It's incredibly essential to life existing in the first place on planet Earth. That's why when they're looking for life on other planets, they're looking for water, because we'll learn more about this in biology next year, but water is like the quintessential part of life that makes life possible. So what does this have to do with water? Oh wait, real quick, you read this in 6.2, but covalent bonds can either be polar. So polar is where electrons are shared unequally between 2 atoms. Think of it like a north and a south pole. Like you have 2 very opposite sides of the planet, and you have different charges of those, right? So that's why we call them polar. And then we could have nonpolar, where electrons are not shared at all. And then there's partially polar. Partially polar, water is a great example of that. It's not super negative and super positive over here, just slightly. Because remember, these electrons are still orbiting around all of these molecules. They're just majorly found around oxygen more. Okay. So your book goes over this in quite a bit of detail. You don't really need to know that much about it for my preference, like on the quiz, but just know that this part is really important to what happens next when we put NaCl in water. So remember, our oxygen has slight negative, our oxygen side has slight negative, hydrogen side has slight positive, okay? So what happens when you put NaCl in water? Let's watch this video. Okay, here's our water molecule. The big blue thing is oxygen, the little green things are hydrogen, right? And then our sodium crystal, we've got purple chlorine, and yellow sodium. And polar charges of the water molecule, positive side with the hydrogens, negative side with the oxygen. And our sodium, remember our sodium chloride atom, we have positive, negative, positive, negative, positive, negative. Repeating patterns like that. Well, we put this piece of salt into water, and these water molecules are going to come and they're going to be attracted to the positive or the negative side, and they're essentially going to pull these individual atoms out of the solid solution, okay? They're going to pull these individual atoms one by one out of that solid form. And you can see here, so put a big negative right here. This is our negative chlorine, and then this is the positive side of the water molecules, okay? So we have positives attracted to the negative, and the opposite, see how the water molecules are reversed? We have the negative sides attracted to the positive sodium. All right, so that's essentially what I want you to know, and you can draw this for your drawing on your lab, or you can draw, a cup and have this in the cup. I just need to see that you understand this concept, okay? This phenomenon is called dissociation. So what I ask students in class is like, well, what's an association? What does it mean to be associated with something? It means to be together, okay? So it means to be together, and when you disassociate it, think about like the sodium chloride as a solid, they're all associated together. But when you put it in water and water starts pulling these atoms apart, then it disassociates. Dis means not, right? Or to undo, like it undoes their association. And so in your cup of water now, you have all these positive and negative ions just floating around in the water. And this is why your ionic solids don't conduct electricity as a solid, but they do when they're dissolved, okay? Because think about it, now we have positive and negatives floating all around in our water, okay? And you stick an electrode in there, and voila, you're conducting electricity between those positive and negatives, okay? That's why it conducts. So now to answer that question about tap water, what can we conclude about the chemical bonds in tap water? Well, essentially, that they're ionic. We have stuff dissolved in the water, and they're ionic because they conduct electricity. So we have calcium ions, we have magnesium ions, and who knows what else is in there, okay? Hope that makes sense. Let me know if it doesn't.